All right, well, welcome everyone to first day of term and first of our series of concrete math seminars. So let me just say a little bit about the series, the concrete math seminar. It's a seminar series where we're aiming roughly for shorter, perhaps informal, but rather computationally explicit lectures. And so I'd encourage anyone who wants to explain some aspect of mathematics to us that's rather explicit and computational, and so that we can see examples that support the various theories. That's the basic orientation. Okay, so I would like to start off with a small series where I talk a little bit about some aspects of algebraic geometry that sort of interest me. And so it'll be a series roughly on curves and surfaces. So that's a very classical topic, of course. So for example, suppose we have a surface, say 2 plus y plus x cubed, not a surface, a curve, minus 3x squared y squared equals 0. So that's a polynomial in x and y, and the plane determines the curve. And if I open up GeoGebra, I can input this thing and it will quickly give me a graph of at least part of the curve, and it looks something like this. Okay, so that's what GeoGebra tells us is the curve. But there's a question here, and I think it's a very interesting question, about what exactly is an algebraic curve. Now the standard answer is that an algebraic curve is the zero set of a polynomial. But that's problematic for me because I have a very computational point of view. So if someone says, well, it's a set of points, then in order to exhibit a curve, I need a set of points, which I'm going to put on my hard drive. So I'm going to ask you for a set of points. And in this case here, for example, you can see the problem because there seem to be a lot of points. And so if you actually wanted to dump all the points onto a hard drive, you'd be overwhelmed by the infinite or unbounded nature of this problem. There's also a second aspect, which is that GeoGebra is actually not really computing points on the curve. The only point that I can easily find is the point when x is 0 and y is minus 2. So the point 0 minus 2 is self-evidently on the curve, but finding any other explicit points is a major undertaking. And if the polynomial was of higher degree, it would be like a PhD program in Diophantine analysis. So finding explicit points on curves is very problematic. And so to talk about a curve as being a set of points which satisfy an equation is, to me, computationally problematic. So I would like to think about alternate ways of thinking about this very fundamental issue in algebraic geometry. That's sort of my overall goal. And what I want to do sort of more specifically is I want to use 19th century thinking. 19th century was really the golden era for geometrical thinking or geometry, and I want to harness that with linear algebra, modern linear algebra, to give us maybe a possibility of a more geometrical algebraic geometry. So algebraic geometry in the last century has made huge strides, much of it from an algebraic point of view. And I think it's time to maybe think about the geometrical side and balancing things a little bit. So I'm interested in geometrical algebraic geometry that we might be able to get by going back to a lot of 19th century classical thinking, which is largely in danger of being kind of lost or perhaps forgotten. So what I want to do today with this first lecture, because it's the first day of term and it's a good place to sort of start in an elementary fashion, I want to actually proceed rather in a simple-minded way and talk about some basic terminology and notation and orientation to affine geometry and projective geometry, and also vector space or linear algebra that sort of straddles the two things. Okay, so the starting point will be a field. So we'll assume in the background that there is a field F. And we're not going to say what this field is. So maybe it's the rational numbers, which I like. Maybe it's a finite field that Mike Reynolds works a lot with. Or maybe it's something else. But I'm not going to be too specific. I'm not going to assume anything about this field other than it's the place where the numbers come from. Okay, so to start, let's start with an affine situation. So an affine K point. And K will be 1, 2, 3, etc. What is that? It's a point of the following form. So A, and it's going to have square brackets, and then A1, comma A2, comma dot dot dot, all the way up to A sub K. Okay, that is what an affine K point is. That's the definition of an affine K point. And when we talk about the space or the type of affine K points, we might use this symbol here, A super K, to denote that we're talking about affine K points. Okay, now let's go to the vector situation. So, the vector situation. So let's define a row K vector. The row K vector is going to be an expression of the form V, round bracket, V1, V2, dot, 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 up to Vk. And it's going to live in V super K. And it's really a 1 by K matrix. So we're using matrix notation here. So the row vector is a 1 by K matrix. That's why there's no commas around. All right? But we also want column vectors. So a column K vector. Let's denote that, say, by F. So F will be, and will be F1, F2, dot, 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 down to F sub K, round brackets. And we'll denote the space of K column vectors by V sub little k. And that's a K by 1 matrix. Now, these are both vector spaces. So for a fixed K, V sub K and V sub K are vector spaces under pointwise addition and scalar multiplication, just as we teach in first year. But now there's row vectors and there's column vectors, and they're sort of symmetrically placed at this point here. Now there is, in addition, a pairing between them. So the pairing is that if we have V and F as here, so then we can take V times F. So we're talking about taking the row vector V1, V2, all the way up to Vk, and multiplying it by the column vector F1 down to Fk, and we're just doing matrix multiplication. So we have V1 F1 plus V2 F2 plus all the way up to Vk Fk. Okay, which is an element in our field. Actually, it's probably a 1 by 1 matrix, to be completely honest. So maybe we should put little brackets around here. Maybe we'll just, okay. But we'll typically just think of that as a number. And that gives us a pairing between these two vector spaces. And that exhibits each vector space as a space of functionals, or linear functionals, on the other. Okay. So this way, V super K can be thought of as a space of linear functionals. So given a V sub K, you can think of that as giving you a function from V little k to the field, or given one of these, you get a function from this to the field. So each space can be viewed as functionals on the other. Okay, great. So we haven't drawn any pictures yet, and I've done that on purpose because I want to separate the logical structure here from any prior geometrical intuition or understanding or physical understanding. So the objects are just these data structures that we write down in these very, very specific way, and we can imagine our computer just being able to check that we either have a k vector or a k point of a relevant size. Okay, so now let's introduce at least a picture. So this is a picture. So we're going to set the picture up in what we might call the affine grid, or affine grid plane. So what we're going to do is we have two axes, and I'm not going to put them necessarily perpendicular because I don't want you to think that this is Euclidean geometry. We're not doing Euclidean geometry at this point. We're doing affine geometry. So what we want is these two axes, we're going to call them the first axis and the second axis. Notice up till now that there's no x's and y's. I just have objects with entries. Okay. So, this is the first axis and this is the second axis. And each of the axes will be labeled with equally spaced sort of coordinates. And they don't have to be kind of commensurable, so maybe the scale appears different on the other one. Okay. Now, let's say we want to illustrate some of the ideas. So, for example, maybe here's the point. Here's the point. That dot represents the affine point 2, 1. And so kind of go up parallel to the axes. So that point there would be that point 3, 5. So these are affine points. So positions correspond, affine points correspond to absolute positions. That's an important idea. So affine points geometrically correspond to absolute positions. Now, what about the vectors? What's the relation there? Well, the idea is that we want vectors to represent displacements or separations between absolute points. So to go back to the general case, if say A equals A1, A2 up to AK, and B equals B1, I'm going to make these actual points, so there's commas between them. Okay, so you can tell from the shape of these things, these are affine K points. Then we define AB to be the vector B1 minus A1, B2 minus A2, dot, dot, BK minus AK. Round brackets, it's a vector. Okay, so to be specific, these are in A super K, and these are actually row vectors, so they're V super K. Although I could have also declared this to be a column vector if I felt like it. Okay, so now we allow ourselves some novel notation. Okay? So we write this also as B minus A. Right, so that's a novel idea, I think. So we've got 2 points. The vector between them, we will allow ourselves to use the difference operator to represent the vector between these 2 points. The affine points themselves have no prior algebraic structure. We are introducing an algebraic structure for the first time now on affine points. In particular, we do not have the notion of sum of affine points. So usually in mathematics, subtraction is a secondary operation. You have addition and then you invert it, you get subtraction. Here, the subtraction has a prior existence independent of a corresponding addition. So geometrically, of course, that will then be represented by, over here, this is, say, A, and this is B, then this thing here, this vector, will be AB, and it will actually be the vector, 3 minus 1, 1, 4, which we also allow ourselves to write as B minus A. And we also write, and we'll also write that B is equal to A plus AB. This is also novel notation. Okay? The idea that if you have a point, an absolute point, and you have a relative object, a vector, which is essentially a difference of points, then you can add the relative position to the absolute point, and you get another absolute point. So, for example, in the example over there, B was 3, 5, A was 1, 2, and then we have the vector. And 1, 4. Okay, and now we turn to the object which is much less familiar to undergraduates, which is the projective point of view. So we want to introduce projective thinking into this sort of elementary situation. And I think it's a very important potential for undergraduates to learn some basic projective geometry. It can be an aid to a lot of very explicit kinds of computations, as I hope to show you. Okay, so projective points. What's a projective point? So a projective k-point. So a projective k-point is an expression of the following form: P equals P0, P1 up to Pk. With some provisos. So first of all, not all P sub I are 0. At least one is non-zero. We're not allowed to have 0, 0, 0 across the board. At least one thing is non-zero. And secondly, we adopt the convention of equality that things are unchanged if we apply a scalar multiplication. So we assume that P0, P1 up to Pk equals lambda P0, lambda P1 up to lambda Pk. For any lambda not equal to 0, we're not allowed to multiply by 0 because then that would contradict that. So a projective point, if you like, geometrically, you can think of this as a one-dimensional subspace of our associated vector space, V super K. Okay, and this is a row object, so we should really call it a row K point. Okay, so it's a row projective row K point. And then there's a corresponding column K point. Notation will equal L. So there we have L equals square bracket L0, L1 up to L, okay. Subject to the same conditions, not all Li are 0, and equal under scalar multiplication. Under multiplication by lambda not equal to 0. So maybe while I have this diagram here, so maybe we can say, so, what do we have so far? So our ambient space is an affine space, and we have this notion of vectors. But the notion of vectors is a kind of a relative notion. So our vector space is actually, our vector space is kind of everywhere. So for example, if we felt like it, we could think about the vector space as being located at A. So there's all these vectors emanating from A, and we can imagine those vectors as being sort of a copy of V sub super 2 in this case. Okay. And what about the projective space? We should give this some names. So let's introduce P super K. That's K-dimensional projective space, and row, and over here P sub K for K-dimensional column space. So over here, we wanted to visualize where is P2 in this story. Well, for example, we could think of P2 as being, say, all the lines through some point. Maybe through A. So if we look at all the lines through A, well actually that would be a P1 because it's, you could take vectors with 2 components, and so the corresponding projective space would be a P1. So that would be P1. Now, so there's some interesting question here that's related to this notion of equality, which is at the heart of things here. So the question is, how do we know, or how can we tell, when our two projective K points equal? So for example, suppose that we have P0 and P1, and we ask, when does this projective point equal this projective point? Well, it's not hard to see. This is just like asking, when is the fraction A over B equal to the fraction C over D? And the answer is when P0 Q1 minus P1 Q0 equals 0. So that little determinant is exactly what we need to compute to check whether the two projective points are the same or not. That's a very elementary way that a determinant appears in mathematics. So it's not appearing here as an area. Okay, the area is actually slightly secondary from this. This is a primary kind of understanding of where the determinant appears. It's appearing here as a condition on when two vectors are parallel or when two projective points are equal. It gets more interesting when we up the dimension. So suppose that we have two projective 2 points, so P0, P1, P2, and we ask when is that equal to Q0, Q1, and Q2. Well, they're going to be equal when so they are going to be equal precisely when we actually need 3 conditions. So I'll write them as this way. P1 Q2 minus P2 Q1 equals 0. P2 Q0 minus P0 Q2 equals 0, and P0 Q1 minus P1 Q0 equals 0. So we need all three of those conditions to check that the two vectors are parallel, or correspondingly the two projective points are equal. In general, in P super K, we need check, well, I guess K plus 1 choose 2 different little 2 by 2 determinants. Let's call them delta ij, maybe like pi qj minus pj qi. We need to check that they're equal to 0 for all possible pairs of indices. And for example, in three-dimensional space, when k equals 3, then there are 4 choose 2, or 6 determinants that need to be checked. And this was the start of a very interesting story, which I'm going to ultimately tell you more about. But so this story of linear algebra really begins, I suppose, with Hermann Grassmann. So Hermann Grassmann was a brilliant German high school teacher who wanted to become a mathematician, but the establishment didn't let him. But nevertheless, he did really brilliant work, which was not understood. But basically, he sort of single-handedly set up what we now call linear algebra. So, although the official story is that linear algebra starts in the early 20th century, actually Hermann Grassmann had the foundations of it, 60 or 70 years before. And his point of view, in his point of view, these determinants play a central role. So, for Grassmann, if you had a matrix like 1, 2, 3, 4, 5, 6, we look at something like that and we say, oh, it's a 2 by 3 matrix. Grassmann would look at this and say, there's 3 2 by 2 determinants here. Right? This is just a recording of the 3 determinants, which are actually exactly the kinds of determinants here that are figuring in the equality between the 2 rows here. And in this the k equals 3 case, that's going to turn out to be crucial in understanding lines in three-dimensional space, which goes quite a lot beyond what we do in first year or second year linear algebra, unfortunately. All right, so motivated by this, we recognize that there's something special exactly in this sort of two-dimensional situation that motivates us to define a product. So we define products of projective 2 points. Okay, so we have P0, P1, P2, cross Q0, Q1, Q2, and we're going to define that to be exactly those 3 things. P1, Q2 minus P2, Q1, P2, Q0 minus P0, Q2, and P0, Q1 minus P1, Q0. And correspondingly, we'll also define the product of 2 column projective 2 points, say M0, M1, M2. That's going to be the row L1, M2 minus L2, M1, same formula. L2, M0 minus L0, M2, and L0, M1 minus L1, M0. Okay, and then one can prove a little proposition exercise is that I should also say that in order for this to work, to be well defined, we require these to be distinct. Okay? And similarly require these to be distinct. They have to be distinct projective points, because otherwise what we've just done over here shows us that the right-hand sides are going to be 0, 0, 0. And we said that's not allowed when we're talking about projective points. Okay, so if we have distinct points, so if P and Q are distinct, then both are incident with P cross Q. And I have to tell you what incidence means. P0, P1, P2 is incident with L0, L1, L2, incident, precisely when that pairing that I talked about for vectors gives us 0. P0, L0 plus P1, L1 plus P2, L2 equals 0. Okay, so now I want to talk about applying why are projective points so important. So there's a geometrical interpretation of the projective geometry, which undergraduates should see, but unfortunately they don't. Okay, so let's look at P2. So P2 can be viewed as one-dimensional subspaces of a three-dimensional vector space. And there's then an important kind of connection in that inside here there's a kind of like an A2. And I want to explain that with a picture. So here's the first axis, here's the second axis, and let's create a third axis. But the third axis will be, say, the 0 axis, because that's what we use for projective points. And so now if you have a scale, so that's 0, 1, 2 on that scale, 1, 2, 3 on that scale, and we're going to put the scale on the 0 axis in a somewhat non-standard place. I'm going to put the 0 out here, okay? And I'm going to choose my scale so that 1 is right there. So that's 1 in the 1, and then maybe 2 is over here. So this is like a three-dimensional space, except that I'm not putting the three axes through the origin. This is really the origin. That's where all three things are 0. But I'm actually looking at the plane where the 0th coordinate is 0, and I'm illustrating that one. And the reason I can do that, and I want to do that, is because now let's say I have a point, say an affine point 2, 1. Then I can associate to that affine point, or think about it, think of this as being sort of in this three-dimensional space. So I can look at this vector here as a vector in this three-dimensional space. That's going to be the vector, 1 in the first direction, and then 2, and then 1. And so then the line through that vector, then the line, that's a physical representation of the projective point 1, 2, 1, which is the same as this vector, except scalar multiples are in any direction are allowed. So what ends up happening is that the affine point, that affine point there, is then identified with this line through the origin from this O that's external to it. Now this is a different way of representing the projective point. So usually, and when I used to give lectures about this, I used to sort of draw a picture like this where you had the ordinary plane there, and then you took the z equals 1 plane and you viewed things this way. So I want to change that point of view to this point of view so that the plane of the board is our usual affine plane, and we're imagining that the origin is out here somewhere along some third axis coming out. And in what direction doesn't matter because it's all just affine geometry. So that what we end up having is a situation where, if you allow me to sort of think of the origin, so the origin is out here, okay? So the projective plane consists of all lines through the origin. And most of those lines will meet this specified 2 plane in a unique point. So there's almost a one-to-one correspondence between projective points and affine points, with the exception of those projective points which are in a plane parallel to this affine plane. In other words, in the plane when the first coordinate is 0. There will be a projective line of such points. So the projective plane is an extension of the affine plane by adding these new things, which are essentially lines at infinity, or points at infinity, line at infinity. Now this has huge benefits for geometry, but surprisingly also for calculus and lots of other geometrical interpretations. So it turns out that if you're doing affine geometry, you often gain quite a lot by enlarging your view to this projective point. And instead of thinking about the affine point 2, 1, you rather think about the projective point 1, 2, 1. One of the reasons is because this is scale invariant. So if there's any fractions appearing here, you can just rescale to get rid of the fractions because you have that extra degree of freedom around to absorb denominators. So the arithmetic kind of becomes integer arithmetic as opposed to rational arithmetic, which is a very nice benefit. But now I want to show you quickly that, in fact, the fundamental problems that high school students wrestle with in terms of planar geometry become almost trivial from this projective point of view. And that high school students, when they make the transition to university in first year maths, they should really learn how to solve these problems using projective geometry. So let me explain that. Okay, so we can solve 2D problems with projective coordinates. How does that work? So the idea is that instead of working with a point, say A1, A2, an affine point, we sort of associate to that a projective point 1, A1, A2. Okay? And the other ingredient is that instead of working with a line, so suppose that we have a line, maybe it has an equation like A plus bx1 plus cx2 equals 0. So for some point x equals x1, x2. It's a variable point. That's a linear equation in the variable point. That's a line in the plane. So to that line we can associate a column 2 point. Which one? We want A, B, C. And the reason why this works is because then the incidence of this on this point lies on this line, precisely when these two are incident. When 1 times A plus A1 times B plus A2 times C is 0. Right? So this correspondence preserves incidence. And also by the way, gives us a physical manifestation now of what a line is. So if somebody asks you, what is a line? That's the same kind of subtle question that I began my lecture with, talking about what is a curve. It's a simpler version of it, but still, you don't really want a line to be an infinite set of points. And so another alternative is to say, well, why don't we set a line to be an equation? That's a reasonable alternative. But now we see a rather better way. Right? We can say a line is just this column 2 vector, or this column 2 point, this projective column 2 point. That is then what a line is. Although that's a slightly bigger picture because there's also some lines that don't correspond to these ones. Okay. But so anyway, so let me show you how to use this technology to solve problems. So for example, suppose we have these 2 points over here, the point 2, 1, 3, 5, and we want to know what is the line through 2, 1, and 3, 5. The line through 2, 1, and 3, 5. Okay, so what do? We compute just the product of the corresponding projective points. We just make the calculation 1, 2, 1 cross 1, 3, 5. So how does that go? So we do it's like a cross product. So there's a 2 times 5 minus 1 times 3, so 10 minus 3. And then there's a 1 times 1, 1 times 1 minus 1 times 5. Check it. It's a silly error here. Okay, that seems to be right. And then the last one is 1 times 3 minus 2 times 1, which is 3 minus 2. So altogether, get square brackets. It's a column thing. Okay, so we get 7 minus 4, 1. Okay? And that corresponds to then the line is, if we want to write down the equation in terms of x1, x2, it's 7 minus 4x1 plus x2 equals 0. We just read the coefficients of that thing down, and that's the line. Okay, as another example, let's take the meet of 2 lines. This is the other thing that first-year students are expected to know when they come from high school. How do you find the intersection of 2 lines? So suppose that we want, this is line L, we want the intersection between L and say M, and let's let M be the line 1 minus x1 minus x2 equals 0. Which is like x1 plus x2 equals 1. So that's, so there's one of our lines in this picture, and the other one is that one there. We're looking for this intersection point. Okay, so what do we do? Well, we convert them both into projective. We already have the projective version of this, so this is 7 minus 4, 1, and what's the projective version of this? Just read the coefficients. 1 minus 1 minus 1, and we take a cross product. Notably the same technology. Okay, it's just a single cross product. It's the only technology that we're really using here. Okay, what do we get? So we get 5, and 1 minus 8, 8, and minus 7, minus 4, minus 3. That's supposed to be a point. Now we want to convert it to an ordinary point, to an affine point. In order to do that, we want to divide by the first coordinate to make that 1. So we get 1 8/5 minus 3/5. And so the answer is that in terms of an affine point, it's 8/5 comma minus 3/5. And finally, another important aspect of this is that it enlarges our view of curves. So we get projective curves from affine ones. So let me just illustrate that with a very simple example. Suppose if y equals x squared, or maybe x2 equals x1 squared, representing parabola. So in order to convert that into a projective object, what we do is we think of the correspondence between a projective point and the corresponding affine point obtained by dividing by P0. All right, so this point here will set to that, and that will satisfy the equation. So we should have P2 over P0 equals P1 over P0 all squared, or P0 P2 minus P1 squared equals 0. So that's the projective version of this equation over here was sort of x2 minus x1 squared equals 0. That's the affine curve, and here's the corresponding projective curve. It's in 3 dimensions, and it's homogeneous. This is not homogeneous, this one is homogeneous, so it really represents a cone. And from now this point of view, this geometrical point of view that I'm advocating, you think of the origin of this 3-dimensional space as being out here somewhere, right in front of you. And lines through the origin correspond to movements of the drumstick. And so what we're doing is we're just tracing out the 2-dimensional surface. It's a homogeneous cone that we get by connecting our fixed origin to all of the points here. And when we do that, in this case, we get something like this. Okay, so something like that. So I've got my origin out here. I'm connecting the origin with all the points on the parabola. You can kind of see that parabolic cross section there. Right. And now the curve is rather this sort of homogeneous surface in 3-dimensional space. But notably, it has one more point on it that the original curve doesn't, because there's exactly one place. As our line is going around, exactly when the line is up here in the vertical direction, then it will no longer be slanting towards the board. All the other ones sort of slant towards the board and meet the board somewhere. But just at the vertical stage there, it'll be straight up and will not actually meet the board except at infinity. So the point at infinity on the curve corresponds exactly to this line through the origin on the cone. This, of course, connects with the classical vision of the Greeks, so that a conic section was just a slice of a cone by a plane. So this is in sort of the first kind of introductory lecture. I wanted to establish notation and sort of definitions more than anything else. And so now we're ready to go to a really interesting situation, which is what happens when you look at lines in 3-dimensional space, for which the story gets much more complicated. So in lines in 3-dimensional space, you'll know that the undergraduates have to write down some cumbersome equation like x minus 1 over 4 equals y minus 2 over 3 equals z plus 8 over 5, something like that. That's the equation of a line in 3-dimensional space that we teach our undergraduates. But it's rather unsatisfactory at a number of levels, because it's, first of all, non-canonical. And so the 19th century people thought a lot about this, and Klein and Hooker saw how to make a more invariant part of the story, and that'll follow on naturally from the kinds of things that we've been doing today. And we'll touch base also with the remarkable connection that Sophus Lee found between the quadric that appears here and what he calls sphere geometry. So it turns out that lines in 3 space and spheres in 3 space have some remarkable connection that becomes visible when you look at it from the right projective point of view. So thanks for listening. Any questions, comments?
So your very first algebraic curve, you wrote a formula for it, and also a question what it is, suggest a bad answer that it's just a set of the points, yeah, and then you suggest that your favorite field is rational numbers. I wonder how many points this curve has over rational numbers.
Very likely few, very possibly none other than the one that I showed you, although an analysis would have to. But typically you cannot expect a lot of rational points, and finding points is difficult. But that doesn't mean that somebody who's interested in geometry over the rational numbers has to dispense with studying that curve. All what it means is that we have to think about that curve in a new way. We have to enlarge our view of what a curve is. That's sort of my orientation. And we cannot be comfortable with the idea of a curve as being a set of points. We need to think in a broader, larger way. And when we do that, we can visualize what that curve is even over the rational numbers. It becomes a very concrete object that's amenable to study.